Okay, welcome to this video AI for work for MA 205 Integral Calculus. Okay, so the objective for this block of instruction is to apply integration to real-world applications. Okay, and that's determining how much work is required to perform an action. So I want to specifically make this connection between estimations and integration for work problems. Okay, so far when we do estimations, we split things based on a delta x, and we put rectangles under the curve and sum them all together to estimate what the area is under the curve. Okay. So this example, I'm given a rectangular tank that's 6 feet long, 2 feet wide, and 2 feet deep, and it's full of water. Okay, so here's my rectangular tank, and it's water, which I know the weight of water, which is in a density of 62.5 pounds per cubic foot. Okay. So what I want to do is I want to essentially put a rectangle under the curve or draw a rectangle in my tank here. Okay, so this represents a slice. Okay, so we're going to pull this slice out of the tank. Okay, now I can visually see that it represents a volume of the tank, some volume of water, and this slice has a constant length and a constant height, and it has this delta x in thickness. Okay, so this delta x is what we're going to determine how thick my slice is. So in this case, let's say that this is 1/2 of a foot. Okay, what I want to do is I want to find the force due to the slice, or i.e. how heavy is my slice. So I set up my picket fence, and I know that the density of water is 62.5 pounds per cubic foot. Okay, so I want to find a force, and I know a force is pounds, so I need to cancel my cubic feet. So I'm going to multiply here by the volume of my slice. Okay, and the volume of my slice is what I see right here, and that's 6 feet times 2 feet times 1/2 a foot, which, keep in mind that this term here was our delta x. Okay, and as I multiply that out, I get 375 pounds. Okay, so this means if I take a half a foot height out of that pool, it's going to weigh 375 pounds. Okay, I want to estimate the work to pump out all the water in the tank. Okay, I'm going to use n equals 4, or 4 slices. So as I go through my delta x calculation, which is b minus a over n, I'm going to take the height of the tank minus the bottom, 2 minus 0, divided by 4. Therefore, each slice will be 1/2 a foot. And if I take this cutaway of the tank, I can draw each slice of my tank. We'll call this the first slice, second, third, and the fourth. Okay. The next thing I want to do is I want to assume that each slice of water moves as a solid unit. Okay. I also want to assume that the distance that each slice moves is going to be measured from the bottom of the slice. Okay. Therefore, slice number 1 has to travel a full 2 feet. Okay, so for the first slice to get out of the tank, it travels 2 feet, and then it's out of the tank. Okay, the second slice will travel 1.5. My third slice will only travel 1 foot. And my last slice will travel 1/2 a foot. Okay, so the most common thing that comes to mind when you think of work is you think force times distance. That's exactly what we're going to do here, except we're going to compute the force times the distance for each slice. So we'll have a total of 4. So we need to sum these slices from 1 to 4, force times the distance. Okay, so the force piece we've already computed up here. This 375 pounds is my force. And the d is the distance each slice has to travel individually. So to compute my work here, I'm going to take 375 pounds times 2 feet. Okay, and this represents my first slice that travels the furthest distance, the slice at the bottom of the tank. The second slice travels 1.5 feet, and the last slice will travel half a foot. Okay, where this was 2, this is the third slice, and this is my fourth slice. So I sum those up to 1875, and my units is pounds times feet, or otherwise known as foot-pounds. Okay, the next thing we want to do is we want to improve our estimate. Okay, we know that the n equals 4 is a very large slice, so we want to improve our estimate by reducing our n. So in this case, we're going to go n equals 8. Therefore, my delta x will be 2 minus 0 over 8, or delta x is going to be 1/4 of a foot. Okay, the next thing I have to recompute is the force due to each slice. In this case, it'll be the 62.5 pounds per cubic foot. And the volume, now I'm looking back up here to my volume of my slice, which remains at 6 feet in length, 2 feet in width, and now the depth, or the delta x, changed to 1/4 of a foot. Okay, and this is my delta x term, and this is the volume of my thinner slice. Okay, and this comes out to 187.5 pounds. Okay, so now to compute the work, I can draw my slices here on my new cutaway. Okay, my first slice has to travel the full distance, 2 feet. My second slice travels the shorter distance, 1.75. So I continue this process until I get to my last slice, which will travel 0.25 feet. Okay. So now I'll compute the work, or the summation of force times distance from 1 to 8 for each slice, in which case each slice now weighs 187.5 pounds times the distance that it has to travel. In this case, the first slice travels 2. Okay, this is my second slice. Will travel 1.75 feet. Okay. Okay, so we'll continue this process until we get to my last slice, 187.5 pounds times 1/4 of a foot. So this work now sums to 1687.5, and again the units are pounds times feet. Okay, and when we compare this estimate from what we had before, we initially had 1875, which was an estimate of how much work we'd done, but now this is a slightly better estimate, okay, because I've reduced the size of my slices, changing that thickness. Okay, the next thing I want to do is find the exact amount of work required, or I want to use infinite slices. So to do that, I'll take my same picture, but instead of drawing infinite slices, I'm just going to draw one. And this one slice is going to be known as the representative slice. And it's drawn on my picture just to represent any slice in the tank. Okay, this slice still has a length of 6, a width of 2, but the height now changes. The height we're just going to call delta x, in which case delta x becomes infinitely small. So delta x before was b minus a over n, but now we want to let n approach infinity. So as I write this formula, I want to take the limit as n approaches infinity, and I still want to take the summation of all slices. I'm just going to have infinite slices. So now I want to figure out how far does this slice have to travel to get out. Okay, and that represents some distance we're going to call x star. Okay, each slice will travel a different distance. Again, just like before, the slice on the very bottom will travel the full 2, and the slice on the top will travel the shortest distance, in which case it travels nearly 0. Okay, so now as n approaches infinity, this delta x gets to be very, very small, or infinitely small. Okay, so that when you think of how heavy this piece of water is, before we started with 375 pounds, and when we divided it into a 1/4 inch of a height, we had 87.5 pounds. So now I need to compute how heavy each representative slice is. Okay, the weight of water is still 62.5 pounds per cubic foot. My slice still has a length of 6, a depth of 2, and now it has a thickness of delta x. And we have to leave it as delta x because it's infinitely small. Okay, so I'm going to take this is now, again, it's still the volume of my slice. And this whole term represents my force. So now I need to multiply it by the distance. So if this is my representative slice, or the force due to my representative slice, it has to travel some variable distance x. Okay, so again, work equals force times distance, and now we have force times distance. But to change my Riemann sum into the integral, we're going to stretch it out into the elongated s, which means the summation of infinite slices, 62.5 times 6 times 2, and this x becomes just x, and my delta x changes to dx. Okay. To set up the limits of my integration, I want to know, again, what is the minimum distance and the maximum distance that each slice travels. So if I look at my pool, if I were to draw this slice at the very bottom, that would have to travel the full distance. It would have to travel 2. And the slice, if I drew this slice up here, it only has to travel nearly 0. And that's my max distance the slice travels. So now I'm ready to integrate, in which case I'm just taking the summation of the force times the distance. Okay, I can factor out my constants, 62.5 times 6 times 2, and just integrate x, in which case I get x squared over 2, evaluated from 0 to 2. This becomes 4 over 2, or the work becomes 1,500 pounds times feet. This represents the exact amount of work required to pump out the tank. And you'll notice that this is extremely close to my initial estimate. When n equals 4, I had 1875 foot-pounds. When n equals 8, I had 1687.5 pounds times feet. When n equals 16, if you carry that out, you'll get 1593.5 pounds per foot. Okay? And thus proving the connection that you can estimate the amount of work required, and then when your estimation, you take the limit as n goes to infinity, you get the exact work required. Okay, so taking estimation becoming more and more accurate to exact.